The lab that we're going to do today is an attempt to verify the law of conservation of momentum in one dimension. What do we mean by that? One dimension? Well, either the x-axis or the y-axis or the z-axis. In all of those conservation of momentum problems that we've done in class so far, we've dealt with north and south or east and west. We've dealt with one dimension. So essentially what we're trying to do is verify the law of conservation of momentum the way we've used it already in class in one dimension. That make sense? Now, we always have to have a problem. I'm going to give you the problem this time because I want you to do this right. I told you a second ago that we're trying to verify the law of conservation of momentum in one dimension. Well, we have to phrase a problem in the form of a question. So how do we phrase verifying the law of conservation of momentum in one dimension? How do we phrase that in the form of a question? Well, there's a few ways you could do it, and there's a few ways that I'd accept. The way that I phrased it, and you can choose to write this down or not, that's up to you. But you can copy it directly from the way that I've done it if you want. I said, is the law of conservation of momentum valid for the collision of two dynamics charts in one dimension? Somebody this morning asked, do we have to say in one dimension? Yes, we do. We have to be as specific as possible. We are not trying to verify the law of conservation of momentum in general. Later this week, you're going to be doing problems where we have a car going north and a car going west. That's two dimensions. We will not show that momentum is conserved in two dimensions. Not today, we won't. We're only going to hopefully show that momentum is conserved in one dimension. So we want to be specific there. Is the law of conservation of momentum valid for the collision of two dynamics charts in one dimension? Here's one that I sometimes get that is wrong. Some people will say, is it possible to verify the law of conservation of momentum in one dimension? That's not the problem. We're not trying to see if it's possible. We're trying to see if it is verified, not if it's possible to verify. Somebody else might say, how do we verify that momentum is conserved in one dimension? That's not the problem. The problem is not to show you how to verify it. The problem is to verify it, right? So we want to phrase it something like this. Is the law of conservation of momentum valid for the collision of two dynamics charts in one dimension? Now, in this lab, as in every lab, we're always going to have three sets of variables: the manipulated variable, the responding variable, and the control variable. How many manipulated variables would we have? How many do we always have? Yeah, just one. Now, it sometimes seems as if there's more than one. Remember one of the quizzes we did where we were changing, what were we changing? The momentum of that toy van when it was stopping, right? Now, that was changed by, well, either changing the mass or the velocity, right? Seemed like there was two manipulated variables, mass and velocity. Not really. There was only one manipulated variable. It was the momentum. So sometimes it seems like there's more than one. There's more than one way of expressing the manipulated variable, but there really is only one manipulated variable. There's going to be one responding variable as well. And that, of course, is the one that responds to the manipulated variable. We change the manipulated variable, the responding variable responds to that. Now, I'm going to recommend to you guys, as you're working in your groups, collecting data for this lab, talk about these things, right? Like, it's okay to talk about the manipulated variable and the responding variable and to agree on what those variables are. It's not okay to copy and paste somebody else's work into your lab report. It's not okay for them to dictate the entire lab report and you just type it out as they dictate. But it's okay to go back and forth about variables and about all of that stuff, right? To help each other out with stuff. That's a good thing. So talk about that as you're completing the lab. The control variables, how many control variables do we have? Like 1,000? Well, yeah, there's like an infinite number of them, really. But we don't expect you to list 1,000 control variables. We expect you to list the important ones, the really important ones. And that might vary. In some labs, it might be one that's really, really important. In some labs, it might be three that's really, really important. In the practice lab you did, it was two that were really, really important. I believe it was, I'm trying to think back to that. I believe it was the mass and the time of 2 seconds, and the mass of, I think it worked out to be 2.5 kilograms that stayed the same through the entire experiment. If we change the temperature, yeah, like technically that's a control variable, but would it really matter? Like not really, right? Not as much as changing the time of the mass would. Here there's going to be two important control variables as well. Especially the control variables, talk about as you're completing the lab with your group. This isn't going to be due for a long, long time because we have a week off. Usually I give 3 days to complete a lab. 3 days takes us till next Monday, but next Monday is a holiday. That takes us to Tuesday. Well, Tuesday is not a holiday for me, but it is for you. So is the whole week. So we're going to make it due the Tuesday after the break. You got a ton of time to do this. The reason I make it Tuesday, by the way, after the break, because I don't want you to have to hand it in on Monday in case you have any questions. I want you to be able to come in and ask me questions on Monday before you submit it. Don't leave this to the last minute, and especially the variables. You will forget stuff. Talk about the variables today as you collect the data. Don't try to think of the variables a week and a half from now as this is 13 days or whatever it is removed from actually completing the lab. Talk about them with your partners today. Try to agree, especially on the control variables today. Next thing you're going to have to do, not the procedure, by the way. You're not going to write down the procedure here. You'll see on Google Classroom a template which lists all the stuff you've got to do, and a rubric which also lists all the stuff you've got to do. Procedure is not one of the things that you have to do. But I got to tell you about the procedure so that you can actually complete the lab, right? Here's how it works. You're going to have two dynamics cards, a blue one and a red one. All of you have to have a blue one, and all of you have to have a red one. You're going to name the red one cart number 1, and you're going to name the blue one cart number 2. For all of you, red is number 1, blue is number 2. I want that for consistency. It makes it easier if you have any questions. It also makes it easier when I go to mark the assignment if we're consistent with that. Cart number 1 has a mass printed on it, as does cart number 2. They will be slightly different, but it's printed on it, so you don't have to worry about measuring or anything. Just read what it says, write it down on a piece of paper. Cart number 1, the red one, you're going to add a mass to it. Now, I don't really care what that mass is. 100 grams, 200 grams. Don't add like a kilogram. Like, don't add that much. 50 grams, 100 grams, 200 grams, something like that, whatever. Just make sure you record what that value is. That make sense? So you should have at this point a mass of cart number 1 that includes the mass that you added, and you should also have a mass of cart number 2, which is just the cart itself. Then you're going to put both carts on a dynamics track. So 2 carts on a dynamics track. The red cart will be at the end of the track. The blue cart will be, I don't know, somewhere in the middle-ish. You're going to give the red cart a little push. The red cart is going to go towards the blue cart. It's going to collide with the blue cart. And because of Velcro, you can't really see it here, but because of Velcro on both carts, they're going to stick together and head off as one. So push the red cart. I don't mean like push. I just mean give it a quick little push. Make it start moving. Make sure that it's moving independent of your hand before the collision takes place. Make sure the collision takes place and they stick together and they head off as one. This is like the first 3 questions we did on that worksheet, right? Where one object collided with a stationary object and then they went off together. It's exactly like those first 3 questions, right? And then what are you going to do? You're going to repeat it again and again and again and again, 10 times. But you're going to repeat it with 10 different initial velocities or different initial momenta for the red cart. And then 10 corresponding final velocities or final momenta for the red cart. You get some data to record here. The mass of the red cart, which remember includes the mass that you added to it, and the mass of the blue cart, which is just the mass that's printed right on there. Remember to title your table. Table number 1. This is table number 1, right? Good title for this table might be something as simple as final velocity of both cars as a function of the initial velocity of car 1. Something like that. Pretty flexible with the title that you put for your table. We just want a brief description of your table when you do that. And then, of course, your first column is going to be initial velocity, and your second column is going to be the final velocity. And you're going to have 10 different rows because you're going to have 10 different trials. Now, how are we going to actually collect this data? Like, we've got to a data table, but we don't actually know how to collect our data yet. Well, you kind of do, because you did this in Physics 20 a little bit. Today's a little bit trickier, not much, but a little bit trickier than it was in Physics 20, because you're actually going to collect data from 2 carts at once, as opposed to 1 cart. In Physics 20, you never use 2 carts at one time. You always use just 1 cart. Not a big one. Okay, we can do this. It just means double the data collection, that's all. So how do we actually collect that data from the carts? Well, we're going to use the app that you downloaded in Physics 20 called SparkView. If you've deleted that, or it's been offloaded because your phone is full or whatever, one person from every group is going to need that app. SparkView, SparkVue. When you click on that SparkView app, it should take you to this screen, and when it does, you're going to click on Sensor Data, that middle box, that middle button, Sensor Data. And when you click on Sensor Data, it should give you some options to connect to. Because there's going to be 8 carts in play here, it might give you 2 or 4 or 6 or 8 different carts to connect to. It might give you other people's carts, in other words, to connect to. You want to make sure that you connect to your carts. They're clearly labeled with the numbers, so make sure you're connecting to your carts, your 2 carts that you're using, your red one and your blue one, and nobody else's. I'm already connected in this screenshot to 2 carts, 294 and 364. Now in Physics 20, you always displayed in the second column position. We're not going to display position this time. We're going to display velocity twice for cart number 1 and cart number 2. Physics 20, we selected position for 1 cart. In Physics 30 here, we're selecting velocity for both carts, for 2 carts. And then that third column, I want you to select table and graph. We need to see that table and we need to see the graph. That's where we're going to get our data from. Now, let's assume that I've performed a trial here. I've given the red cart a little bit of a push. It's moved towards the blue cart independent of my hand, and it left my hand. It's moving on its own toward the blue cart. It hits the stationary blue cart. They go off together as one. By the way, if they don't stick together, if the Velcro doesn't quite work for whatever reason, it's okay. Just stop and repeat the trial. Don't count it if they don't stick together. They stick together. We have 2 graphs plotted real time that look like this. This is beautiful. This is exactly what I want to see. What do these graphs represent? Well, you can see that both carts initially had a velocity of 0. In other words, I pressed the start button and neither cart was moving right away. That's fine. I don't care about that. You remember in Physics 20, there was always a little bit of a delay in starting. Do you remember that? You'd press the start button, and then it would take a couple seconds to actually start collecting data. You know, it's okay to have 0 velocity initially. Press the start button, wait a couple seconds before you push it. And then after you see data starting to form on your graphs, then give it a little bit of a push. That's going to result in 0 velocity here. Who cares? That doesn't affect us at all. Okay? And then what happens here? Oh, look, the collision must be taking place right here. You see that? Something's happening to both carts. The red cart is speeding up as I push it. It reaches a peak velocity, and then the collision takes place. And we can see the collision takes place because the blue cart starts moving, right? Blue cart's not going to start moving if the collision hasn't taken place. And then they head off together as, what does this look to be, about 0.4? And the red one looks to be about negative 0.4. The red one's going backwards in order to connect. That will be the case. That's okay. They're both moving at 0.4. Yeah, why are they both moving at 0.4? Because they stuck together and they're heading off as one at 0.4 meters per second, right? A little hard to read the values off of that graph. So what we're going to do is actually read it off of the data table here. Look over here at the data table. That's why we're displaying the data table and the graph. Look over here at the data table, okay? Look at the blue card here. Card number 2, 0, 0, 0. Not moving, is it? This is before the collision took place. Tell me, which data point number, 43, 44, 45, 46, 47, which data point did the collision take place? When did the collision begin to take place? I'm going to say data point 47. Look, why data point 47? Because that's when the blue one starts moving. You see that? When does the blue one start moving? When it's hit. We don't want the velocity at when it's hit. We want the velocity immediately before the collision takes place, right? We want V1I right here. 0.601. It says negative 0.601. Just drop the negative. V1I is 0.601 because that's the velocity of the blue card, the red card, just before the blue card started moving. 0.601, and then, oh look, the speed of the red card goes down. Why? Because it just hit the blue card, and the blue card is starting to move here. You understand how we're going to determine what the value of V1I is? It's the last velocity for the red card before the blue card begins to move. And it should be the maximum one. It should be the highest value. Get it? We're going to record that right here, 0.601 meters per second. And then we're going to record VF. Well, how do we find VF? What do we know about the final velocity of the red card versus the final velocity of the blue card? What do we know about those two velocities, Lincoln? They will be the same. So what we're looking for here is the first point, the first data point, 49, 50, 51, 52, 53, for you guys it might be 173, whatever data point where they both start moving at the same speed. Does that make sense? So what do we got here at 49? 0.44 and 0.191. Nope. 0.377 and 0.300. Nope. 0.358 and 0.356. No, but they're really close now, right? Really close. Sometimes they won't work out to be exact. We can live with a 0.358 and a 0.356 if none of them match up perfectly. But if we have two of them that match up exactly, that's what we want to go with. Look at that. 0.365, 0.365. That's the final velocity immediately after the collision takes place, 0.365 meters per second. So now we're going to go in and record 0.365 meters per second as my final velocity of both carts. Then just repeat it. Just send cart number 1 down with a different initial momentum or a different initial velocity and see how the final momentum or the final velocity responds to that. Do it again and again and again. How many trials should we have? 10. If we start running a little bit short of time, we can maybe adjust that a little bit, but for the most part, we're going to expect you to have 10 data points.